So thanks a lot for the invitation to the workshop today. I've really been enjoying the talks so far. The talk that the paper that this talk is based on, I wrote about a few years ago as a master's student, and there are some things that I've changed my mind about now. So what this talk will be is me going back to that paper and keeping from it what I really think to be essential. And it's possible that I'll speak of things that some of you already know, maybe even know better than me. But I think even for those of you just figuring out the way I think about these kind of topics and how they relate might also be useful. So what I want to do in this talk is that I want to define computational phenomenology, at least in the way I propose to define it, in analogy to neuro-phenomenology. So I'll start by introducing that quickly. So then I'll use it for my definition. I will then quickly apply it to deep learning with two small cases just to kind of show how the method could be used. And then I'll highlight some advantages of this method according to me. So when you go about to study cognition, there are two kind of stances among maybe many others that you could take. Something like scientific naturalism. I was not sure how to call it actually. You could call it in a lot of different ways. Third perspective, maybe also. So where you rather look at the brain of a person, maybe also the body of the person. And then on the other side, phenomenology, where you would rather start from lived experience, describe it, and try to find some structural invariants or some habits that kind of structure it. So defined like this, just as methodologies, everything can look fine, but as you may know quite quickly, these stances can come to a clash, especially as soon as people have like an ontological commitments that come with the stances, or at least commitments towards what should count as a kind of the a priori structure of cognition. So the story with scientific naturalism could go something like the starting point of studying cognition should be studying the brain. What we experience in the end should be reducible to what we see in the brain. And then phenomenologists might say, no, 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 the starting point should be lived experience and objective thought, to which science and neurosciences belong. They're only at the horizon of experience, and the kind of things we discover there, they can never go against what we discovered with phenomenology. And so according to me, the kind of founding idea of neurophenomenology is to just kind of bracket these kind of ontological commitments that can lead to a clash and simply say, okay, we have two kind of methods from which we can gather data considering cognition. And using Bitball, I like to call these kind of two points, two sources, epistemic sources considering cognition, because they give us sources of data considering cognition. And then the idea of neurophenomenology is to allow a kind of circulation between these two sources and to identify structural invariants that hold true considering certain cognitive processes. And already quite quickly when this was introduced, I think around 96 or something by Varela, people also found a role that the computational could play. And the idea was that formal or computational models can serve as a kind of neutral ground between our two sources, epistemic sources of cognition. And so the structural invariants we could discover, we can simply formalize them in a computational language. It helps us to kind of write down our results on a neutral ground. And so one of my key claims is to say that with the advent of AI and more particular deep learning, the computational has become more than just a tool to formalize, but that has also become in its own right an almost independent epistemic source of cognition from which we can gather data concerning cognition. So for example, when we train a deep neural network on a lot of data, so the example works better if it's a big model and a lot of data, we don't really know beforehand what behavior that model will exhibit, what weights it will have, what activations it will show on particular inferences. And so all of these can be seen as new data considering cognition. So a simple example to kind of highlight what I now call these three sources of information considering cognition. With an example would be, let's consider the task of finding your way home. You could kind of think about it as a phenomenologist. Hubert Dreyfus likes to speak of this example because his thesis is that to find your way home, the best model of the world is the world itself. So when you see that particular tree on your way home, you know that you have to turn left and you don't have to rely on a map. But there was just a small example to kind of give you the intuition that from like lived experience itself, you can start to think about the cognitive process of finding your way home. Then, of course, the kid that finds its way home in this way, you could have a series of brain activations. So this informs you, gives you some kind of data. And now the new source would be to train a deep learning network or another A model, maybe in a reinforcement learning setting. Maybe you could even have it walk this precise or navigate along this precise path. And then you could also kind of use the sequence of activations of your network, of behaviors, and of weights as some kind of data, considering the cognitive process of finding your way home. And so my claim that the computation is now a source of cognition, I think I argue that it has already been realized for quite a while by computational neurosciences. And I think here a paradigmatic example is this quite famous paper from Yamin Carlo, where they take a deep learning network, they train it to classify some images. So this you can see in point one. The network becomes really good at classifying, I think, faces from other objects. I'm not sure anymore. And then in a second step, it shows these images to the trained network. It gathers the activations of the network. It then also shows the images to some monkeys and kind of keeps or records the activations of the monkey brains. And it uses the activations of the deep neural network to predict the activations in the brain. And this model is really good. It's way better than training a model from scratch on predicting brain activations. And so here you can really see that considering the cognitive process of perception or classification and perception, these researchers, they considered that both the computational and the neuroscientific source kind of can provide us some information on the cognitive process and that they can be compared and that that it's helpful in some situations to compare them or use the one to predict the other. And so my idea or proposition is to define computational phenomenology in analogy to neuro-phenomenology and to computational neuroscience, cast in this kind of very epistemic and ontological commitment-free way. So you bracket the neurophysiological, you bracket in a sense kind of the hardware of cognition, like where you think it happens in the physical world. And then you kind of let the two sources of cognition that you have, the computational and the phenomenological, dialogue free of any other constraints. A recipe for this could be to pick a cognitive process, to describe it from lived experience as a phenomenologist, to take a computational model, train it on an analogical computational task, and then see if the models learn similar tricks and use that to identify some structural invariance. And so, importantly, this method cast in this way, it doesn't suppose in any way or neither implies in any way that AI models are conscious. It just uses the computational as a kind of source of information given cognition. The idea is that the way the model learns to solve a given task, maybe we learn to solve it in a similar way. And so now I have two small examples involving deep learning models. Maybe first the question would be, why would we even turn to deep learning? And the idea is that arguably the models that are best at solving cognitive tasks today are the big deep learning models. And so intuitively, they might give us most and the best data considering cognition. And so it's only natural, I think, to at least also turn to deep learning. And so the example I have in mind is an experiment, I think from Gerb and Goldstein, I might be wrong here, that is commented by Merleau-Ponty in the Phenomenology of Perception. So the experiment goes in this following way. There's a subject that sees a room through a mirror in such a way that the room is tilted by 45 degrees. This is what I want to represent with this image. And after 10 minutes of looking at the room through this mirror, something quite unexpected happens, is that suddenly his perceptual field shifts and tilts to become horizontal again. And so Merleau-Ponty considers this case and he wonders how this was made possible. And notably, he wonders how the lived body, by which mechanism it might have identified that the kind of scene that the person sees is not in the correct orientation. And so the hypothesis he makes, or maybe even the thesis, because he gives a lot of arguments for it, is that it's actually the objects in the scene that we have often seen that are shown in a wrong orientation and that kind of call a virtual body that one would need to kind of live and interact in the tilted scene, and that kind of constitute anchoring points for the identification of the tilt, and that this then allows the tilting to be corrected. He says it is as if certain objects, the walls, the doors, and the man's body in the room, determined as oblique in relation to a given level, take it upon themselves to provide the privileged directions, acting as anchor points and cause the previously established level to shift. And if we now consider RodNet, which is a model that is trained to predict by how many degrees an image was tilted. So for example, it's given this image and it's asked how much, by how many degrees was this image tilted? Here it's 0, and then here it's, I don't know, 45 or 270, or no, 90 or 270. And with these attention maps, we can see what the model pays close attention to, or what kind of input patterns were particularly important in its decision. And we see that, unsurprisingly, in a way, it learned a similar trick. It learned to kind of focus on particular objects that often appear in the training data. And so here it looks at faces, and these are the anchor points in a way that help it to identify the rotation of the image. And I mean, so far it's only a small example. It's only meant to illustrate that we can find from the computational source and the phenomenological source cognitive tasks that were solved with the same trick, a very simple trick. So we have identified a kind of candidate mechanism of how we learn to detect the rotation of a visual field or of an image. And we have done so without ever looking or thinking about the brain. And then my second example is with Sartre and Deep Dream. So Deep Dream is a technique used to generate some fun images and learn a bit more about deep neural networks. It goes like this. You take a model that you already trained on identifying images and that got quite good at it. You then fix its weights. So you don't want the model to learn anymore. You pick a certain label and then you perform gradient descent on the image. And then you get something like that. So in this way, you get the image that maximally activates the label banana. And if you do this for other labels, you get the following image, a heart, beast, measuring cup, ant, starfish, etc. And so Sartre, in the imaginary, he thinks a lot about mental images that we can form with imagination. And his thesis is that these images, they are often qualitatively defined, although qualities kind of flow around in the mental image that you have, but quantitatively undefined. And before you read the text, I'll give you the example that he discusses. So he says, imagine in your head, and I'll ask you to do it too, the Pantheon. It also works with the Parthenon in Greece, so the temple, the Greek temple. And now that you imagine it, try to count the number of columns that you see. So it might be that you're not able to count any number of columns, or at least that's what usually people report. So the idea is that you have a mental image that is qualitatively defined, but quantitatively undefined. And so there's this citation, maybe I won't read it, but there's this idea of a non-divided nature and a system of fragmentary views. And if you add that to what I just told you, you get a description that I think is quite close to the images that we have here. So here we have again employed computational phenomenology, and we have kind of identified shared properties of images generated by the computational or described by the phenomenological. Maybe one thing that I can add is that you could also, and I do this a bit in my paper, use this as a starting point to formulate a kind of hypothesis about how imagination might work. So you might say, oh, okay, so we have some circuitry that or some habits that allow us to identify things in perception, for example, identify bananas. And then it might be that imagination kind of re-employs these tracks, these habits in a kind of a different way. And so that could explain why the kind of properties that we get from imagining or forming mental images are similar to those of deep dream. My point here is not really to kind of argue for or against that hypothesis. It's more to show that computational phenomenology could also then be used to formulate these kind of new hypotheses about how cognition might function or what habits might underlie certain cognitive processes. So the advantages of computational phenomenology, they allow you to discover new structural invariants while letting the kind of neurophysiological source on the side while bracketing that question. The computational could inform phenomenology and vice versa. So maybe you train a model like RodNet and you identify another trick that it used to identify the rotated images. And then you tell Merleau-Ponty, oh, look, the model, it kind of found this trick. Can you check if maybe in lived experience we also use a similar trick? And then the other way around, maybe phenomenologically, we can wonder about the mechanisms by which we learn, and we can use that to build different AI models. I mean, of course, the possibilities are wide cast in this general way. And then I think a last point is that today, often deep learning researchers, their stance is very much a scientific naturalism stance, which I don't think is a problem at all. I think it makes sense. But sometimes when they compare these brain activations to deep learning models and it works so well, it makes them very emboldened to make very strong metaphysical claims about, I don't know, the being sure that the brain is the starting point of kind of everything we experience and that we live in a brain-generated delusion or things like that. For example, so these examples of reckless metaphysics, that's how I like to call them. And so I think that we now have another kind of methodology. I mean, you could also find other ones with which you can say, oh, okay, of course, we learn through the brain, and so we can compare that to deep learning models, but now we can also compare it to how we learn as observed from phenomenology. We have kind of another game in town, and this can maybe serve to counterbalance these kind of cases of reckless metaphysics. And that already concludes my talk. I'll leave you also with the three sources that we have discussed and the three methods that combine these sources.